Okay, in today's session, we will discuss about minimization and what is minimization, how it is, um, why we do it, how it is done. That's what we will discuss here. Minimization of a DFA. So first is what is minimization? Minimization is something where it will reduce the size of the DFA by reducing the number of states. Now, how it is done? Let's take an example here. This is a DFA and this is the minimized DFA. Both DFA will accept the same grammar, same language, but you can see number of states are less in the minimized version. Here the number of states are six. In this case, number of states are only three, right? So if you see here, there are some states that are merged together to become a new state where you can see Q3 Q0 and Q3 is a merged state. This Q0 and Q3 is merged together to become this. Here Q1, Q2, Q4 merged together. Now they are not merged directly. They follow some same transitions. That's why they are merged together. You will see how this will be done. But the main thing here is what is minimization? Minimizing the number of states from the DFA, but still it accepts the same grammar. Okay. And here one more thing is if you see let's move further and then we will get to the same point again. So first thing is what is minimization? It is somewhere with which where we number of states will be reduced. Okay. Now next is why minimization is needed. Why minimization is needed? Because it will simplify the whole DFA and it will be simple to understand because the states are minimum. It will be more efficient because states are less, so less memory it will take, and also the computational power needed will be also less because states are less. Again, third is the minimized version of the DFA will be a unique version. Okay, it says uniquely defined. That means using this six states, if you create a DFA, a different DFA with somewhat same transitions you can able to create a DFA which is not same as this one, but that will accept the same grammar. But using only three states, it's not possible to create a different altogether DFA. That means uh, this DFA will be a unique one. And the DFA, the second DFA, if you minimize that DFA also, it will also give the same DFA. Maybe the names of the states will be different, but the language it accepts, the grammar will be same. So the minimized version of the DFA will be unique. Now that being said, um, we know what is minimization, why is minimization needed. Now we'll see how to do it. Now there are three main steps in minimization. First is removal of unreachable states. Now, what is actually removal of unreachable states? If I take an example of a DFA where let's say Q naught is a start starting state, okay, and Q naught let's say transitions to Q2. Q2 will be the second state on input of 0, okay, and Q2 transitions to let's say Q3, which is an final state on input of 0. And to make it full, so let's say from Q1, the one input transition will be to itself. From Q2 also, one will be the input one will be transition to Q0. From Q3, the one input transition will be so Q0. Now this will make the DFA whole. Now this DFA is accepting a string which ends with 00. If you see here, 00, it goes to Q3. If any any other input comes, let's say 1, it goes to Q not again, right? So any input which consists 00 at the end, it will be accepted by this DFA, right? What if this DFA consists another state which transitions to Q3 on input 0 and itself on input 1? Now, this is the DFA, right? But this is still a valid DFA. It accepts the same grammar. But this state you see here, this doesn't add any value to the DFA. Actually, it's an unreachable state. Why? Because from Q0, if you try to reach Q4, it's not possible. If you see here, it Q from Q0 you can reach to Q2, Q2 you can reach to Q3. From Q3 you cannot reach to Q4, right? From any state you cannot reach to Q4. That's why it's an unreachable state. So if it is an unreachable state, that means there is no need of this state in the DFA, right? So that is unreachable state and it should be removed in order to minimize the DFA, right? Now, second is merge equivalent states. Now, what is equivalent state and how to merge it? Let's take an example of, let's say, um, this is a DFA Q1. Uh, this is a start state. Let's say Q2 will be the second one, and let's say Q3 is there, and there's a final state Q4. Okay, here Q1 transitions to Q2 on input 0, Q1 transitions to Q3 input 1, Q2 transitions to Q4 on input 1, Q3 transitions on input 1. So this is done. Um, let's say Q2 goes to itself on 0, Q3 also on 0, and Q4 as well on both the input, it stays to the same one. So this is a DFA where you can see Q1 is transitioning to Q2 on 0, Q1 is transitioning to Q3 on input 1, and Q2 and Q3 both are transitioning to Q4 on input 1, right? So transition of Q2 and Q3 is same because they're on that same input, they're transitioning to the same state. What if I do this Q1, the start state, Q2, Q3? Now this is a merged state, right? And it goes to Q4 then. Now the transition from Q1 to Q2, Q3 will be this transition and this transition. That means on 0 and 1 both, it will go to Q2, Q3. And Q2, Q3, they kind of goes to itself on 0 input. And for 1, it goes to the final one. Final has this 0 and 1, that is done. But if you see here, by merging this, the DFA is simplified. Also, it accepts the same grammar, right? So this is how you merge states. So that being said, next is the methods of um, DFA minimization. Now, there are two methods. First is table filling algorithm. Um, Second is partitioning method, which we will see now in this session. Now, in partitioning method, what happens is there will be two groups created, which will consist. Uh, First group will consist final states, all the final states. Second group will consist non-final states, and we will check the equivalence of different states with together and divide them into different sets. Now, let's take an example to understand this. So, here in this example, you can see a DFA is constructed, a diagram is there, you can see, and the transition table is there. Okay, so the first thing that needs to be done here is removal of unreachable states. If you see here in this diagram, there is no state which is unreachable. You can go from Q0 to any state. Let's say Q0 to Q1 possible, Q1 to Q3, Q1 to Q4, here Q0 to Q2, Q2 to Q5, Q2 to Q6. So every state is reachable, so there is no need of removing any state. First step is done. Second is merge equivalent state. Here we will use partitioning method, and the first thing that we need to do is check the zero equivalence. Now, what is zero equivalence? Zero equivalence. In zero equivalence, we group final states and non-final states together. Now, how it is done? Let's say here, if you see, what are all non-final states? Non-final states. If you see in this one, Q0 is not final state. In this, it's given, right? No. So Q naught will be non-final state. Q1 will be a non-final state. Q2 is final state. Q3 is non-final state. Q4 is non-final state. So these are non-final states. First group. Second is for final states. Final states, the first final state is Q2. Here it says yes. Q4 is, sorry, Q5 is the next final state, and Q6 is the last final states. So we have divided all the states into two groups, non-final states and final states. Now these two groups, we will um, check the equivalence in the next step. Next step is finding one equivalence. Now here, how to find one equivalence? We will check equivalence of states in that group. How? How to do it and what is actual equivalence? Let's see. So let's take an example where let's say states are A, B, C, and there's another set E. Okay. Here, if I need to check equivalence of A and B, I'll check the transitions. Let's say A's transition on 0 is goes to B and B's transition on 0 goes to C. Here, if you see on transition 0, A goes to B, which is in this set. A on transition 0 goes to C, which is in this set. B and C are in the same set. So we can call them as equivalence. A and B has equivalence because their transitions B and C is in the same set. Okay. What if A's transition on input 1 goes to C and B's transition on input 1 goes to E? Now here C is in this set. Okay. But here B transitions to E on input 1, E is not in the same set, right? So this is not equivalence. So B and A and B is not equivalence. Even though in the first step we found the equivalence, if in the second step equivalence not found, we will consider A and B as two different set. So A will be in a different set and B will be in a different set. Now we need to check equivalence of C also with A or B and or A and B. So we can maybe merge them into this set or we can create a new set for C also. It depends on the transition. But in our example, we have different states. So let's take equivalence of Q0 and Q1 first. So if I take Q0 and Q1 and I'll need to check the equivalence and see if they belongs to the same set or not. So the transition of Q0 and Q1, I'll check the transition table here. You can see transition table and in that transition table, uh, the input 0 we will check first. First, let's start with 0. For input 0, Q0 transitions to Q1, okay, and Q1 transitions to Q3, okay. Are Q1 and Q3 in the same set? Yes, Q1, Q3 are in the same set. So this is an equivalence. Okay, right. Now we will check equivalence for the input 1 as well. Okay, we need to check for every input. So input 1, Q0 for input 1 goes to Q2, right? I'll write Q2. And Q1 for input 1 goes to Q4. I'll write Q4 also. So if you see here, Q0 goes to Q2, which is in final set, right? And Q1 goes to Q4, which is in non-final set. So they don't prove equivalence, right? That means the final set that is going to be created, it will have Q naught in a different set and Q1 in a different set. Okay, the set is not completed yet, but we will consider them in a different sets. Okay, now next equivalence. Let's say for Q3, we need to check with Q1 or Q0. Anyone we need to check with both of them if possible. If the equivalence of Q3 is there with Q0, that means we don't need to check with Q1 because Q1 is already not equivalence. So I'll try with Q0 and Q3. Okay, for input 0. we need to start with 0. So Q0 on input 0 goes to Q1, right? And Q3 on input 0 goes to Q3, correct? Q1 and Q3 are in the same set, so they prove equivalence, correct? Now let's take Q0, Q3 for input 1. For input 1, Q0 goes to Q2, okay? And Q3 goes to Q3, right? Now Q2 and Q3 are not in the same set, right? Q2 is in this set, Q3 is in this set, so they don't prove equivalence. So these are being done. Now, what is the next step? We need to check the equivalence of Q3 with maybe Q1 or Q4 also. We can directly take Q4 because we need to eventually check for Q4 as well. So let's say for Q3 and Q4, for 0 input, Q3 goes to Q3 only and Q4 goes to Q4. Okay. Q3 and Q4 both are in the same set, so this proves the equivalence. For Q3 and Q4, for input 1, Q3 goes to Q3 and Q4 goes to Q4. Again, equivalence proved. So Q3 and Q4 can be in the same set, but not with the Q0, right? So what we can do is we can create a different set for them, Q3, Q4. Okay. So this is being done. We need to check for final states as well. So let's take Q2, Q5. In Q2, Q5, we need to check the equivalence for input 0. Okay. For input 0, Q2 goes to Q5 and Q5 goes to itself, which is Q5. So this proves equivalence. Let's take it for one input as well. So Q2 goes to Q6 here and Q5 goes to Q5. So this also proves the equivalence because Q5, Q6 both are in the same set. So Q2, Q5 can be in the same set. Q2, Q5. If we check the equivalence of Q5 and Q6 for input 0, Q5 goes to Q5 and Q6 goes to Q6. Here you can see Q5 goes to Q5, Q6 goes to Q6, and this proves the equivalence. For second input 1, Q5 goes to again Q5, Q6 goes to Q6. This also proves the equivalence. So that means Q6 can be there in this set. So this was one equivalence. That's what we found out. Now next is two equivalence. We need to do find the equivalence again and again until we get to the point where no further division is not further division is not possible. So in two equivalence, we need to check the equivalence of Q3, Q4 because these are already different sets. So for a single state, we don't need to check. For Q3, Q4, let's take equivalence at 0 or 0 input. For 0 input, Q3 goes to Q3 only and Q4 goes to Q4. Okay, so this proves the equivalence because Q3 and Q4 are in the same set. Now this time you need to consider this groups also groups only because this is how the division works here, right? Now the second thing is for input 1, right? For input 1, Q3 goes to Q3, Q4 goes to Q4. This also proves the equivalence as Q3 and Q4 are in the same set, right? So this done. Here at the end, we can see that the sets will be Q0, Q1, and Q3, Q4. So no further equivalence we need to check for them because they are as same as the previous one. So this is done. What about the final ones? Final ones are the same as the final one previous in the previous equivalence, so they are kind of the same. But here one thing here is if you check the transition of Q2, it goes to Q5 for 0 transition, and it goes to Q6 for 1 transition or once transition. But Q5 goes to itself on both the transitions. Also, Q6 goes to itself on both the transitions. So we can do one thing. We can create a different set for Q2 and different set for Q5 and Q6 because they have the same behavior, right? Now, if you see 1, 2, 3, 4, 5, 5 different sets we have created. Now, using those set, we can create a transition table. The previous transition table you can see right here. Now, the next transition table will be here for input 0 and for input 1. Okay. The first state will be Q0, which is a start state, right? So Q0 on input 0, it goes to Q1, right? So Q1 is in this set. So this will be the first transition. Now Q0 for input 1 goes to Q2. Now if you see Q2, Q2 is here, which is also valid, right? Because it's a different set. So this transition is done for Q0. What about Q1? Q1 here. Q1's transition is goes to Q3, right? Q3 is in this set. So this set will be a single state now. So Q3, Q4 is a single state. So on Q1 of 0 transition, it goes to Q3, Q4, right? Now Q1 goes to Q4 for one transition, and as they are both together now, so Q3, Q4 will be the transition, right? This is done. What about Q2? Q2 is a final state, right? So I'll write maybe star here. So Q2 is a final state where it transitions to Q5 for input 0. As Q5, Q6 are the same here, so Q5, Q6 will be the transition. And for input 1, it goes to Q6. But Q6, Q5 same, so we will write Q5, Q6 again. So this is a single state, right? Now after Q2, we'll see the transition of Q3, Q4 because it's a single state. So for Q3, Q4, the transition is happening for Q3 goes to Q3 itself and Q4 goes to Q4 itself. But as they are the same one, so we will write directly Q3, Q4 also for one Q3, Q4, right? Because the transition of one is also for Q3 and Q4 is Q4, which is a same state. After Q3, Q4, the next state is Q5, Q6. Q5, Q6, a single state which is also a final state, right? If I write Q5, Q6, this is transitioning to itself again, same as the previous one. So this will be Q5, Q6, and Q6, Q5, Q6 goes to Q5, Q6 for one transition as well. So it will be Q5, Q6 again. Now this is the transition table after minimization. If you see, this was the previous transition table, and this was the DFA, the non-minimized DFA. If I create a DFA using this transition table, this DFA will look like this. Okay, the transition table is right here, and the DFA which will constructed by minimization will be this. And here you can see there are less number of states. We have merged uh, two different states together, or we can say two pair of states we have merged. So there are two less state in this DFA, which is a minimized form now, right? Now here, this is how you do minimization. Again, let's go through the steps. First is the removal of unreachable state, right? First was this step. Second is the merger, right? Now how to do the merge? Using partition method. Now, how this partition method works? In this partition method, you'll find the equivalence, different equivalence. Let's say zero equivalence first, and in zero equivalence, you'll divide the states into two groups. First group will be of final states, and second group will be non-final states. So after doing that, you'll find one equivalence now. Now, what is one equivalence? You'll check the transitions for each state or each pair of states. You'll see their transitions. Are they happening in the same set or not? Right? Maybe in the final state or non-final state. If they're happening in the same set, that means they are equivalence. If not, they're not equivalent. So we'll create different sets for them altogether. Right? So this is how one equivalence works. If after that also there is a possibility of a division. You will do two equivalence, and in this two equivalence, again the further division will happen. You'll do it until you reach the state where the previous equivalence final sets are the same as the current one. So at the time you will stop and the merger will be done. Now you will create a transition table for that. So third will be creating a transition table after merging the states, and using that transition table you can create a DFA which will be a minimized DFA, right? So this is how the whole process of minimization of DFA works. So there is a problem given here. You can try to solve this. This is the DFA diagram, and also you can see the transition table given here for the same, and try to solve this. Um, anyway, I'll attach the solution with the video, and that's it. Thanks.